Hi friends, and welcome to this second session on number systems. In this session, we would be discussing about the nomenclature of division, some divisibility rules, important principles of divisibility, and some rules on remainder, and finally finding the last digit. So let's get started and come to nomenclature. So we say let's have two numbers a and b. When we say a is divided by b and gives c, what do we mean? We say that a is dividend, b is divisor, and c is quotient, right? So this is the basic nomenclature. Let's take an example to understand it. Let a and b are 6 and 3. So here 6 would be dividend and 3 would be divisor. And when we divide 6 by 3, what we get is 2, and 2 is called the quotient. Now if instead of 6 a is 7, we would get a remainder as well, right? And we can write 7 is equal to 3 into 2, which is divisor into quotient plus remainder. So in general, we write dividend is equal to divisor into quotient plus remainder. This you have to keep in mind, and this would be used in some of the questions. Or in short form, we would write d is equal to p into q plus r, where we denote divisor by p. So we would be using this form throughout this lecture. Now let's see how an examiner can set questions based on this, right? So very common question is find the largest 4-digit number which is divisible by 15, or largest 3-digit number, or largest 2-digit number, or largest 6-digit number, or whatever, right? Divisible by any of the number. So I'm taking 15 as that number. We know that the largest 4-digit number is what? 9999. So any number which would be divisible by 15 exactly should be either 9999 or should be less than 9999. Now how do we proceed about it, right? Let's divide 9999 by 15, right? Let's divide 9999 divided by 15. What do we get? We would get a quotient and we would get a remainder. If you divide it, if you do the calculation, the quotient is 666 and the remainder is 9. So what we can do is we can write 999 is equal to 15 into 666 plus 9, right? Now remainder is what? Remainder is just the residual, right? When we divide a particular number with another number, if it is not perfectly divisible, we get a remainder. Here we get 9 as a remainder. If we subtract 9 from 9999, what do we get? 9990. And on the right hand side, we would get 15 into 666, which is a perfectly divisible number by 15, right? Thus our answer becomes 9990. This is the largest 4-digit number which is perfectly divisible by 15. Now again, if an examiner asks what is the smallest 5-digit number perfectly divisible by 15, how should we now proceed for this question, right? Again, we would take the smallest 5-digit number, which is 1 followed by 4 zeros, right? This is the smallest 5-digit number. Again, we would divide it by 15 to get a quotient of 666 and a remainder of 10, right? Again, we would write 10,000 is equal to 666 into 15 plus 10. Now if we subtract 10 from both the sides, what we would get is a 9990, which is a 4-digit number. But what we want is a 5-digit number. So instead of subtracting 10, can we do something else? Yes, we can. We would add a 5 on both the sides. Let's see what would happen if we add 5. Here on the left hand side, we would get 10005. On the right hand side, we would get 666 into 15 plus 15. We'll take a 15 common. What we would get is 667 into 15. This shows that again 10005 is perfectly divisible by 15. Hence 10005 would be our solution. This is how we use this property and get a number which is perfectly divisible by any other number by either adding the remainder either adding subtracting the remainder or adding a number so that we get a number which is perfectly divisible by the divisor, right? This is how we proceed for such kind of questions. Such kind of questions are very common, and I hope that you would do it well after understanding the concept. Now let's go to the next concept, which is divisibility rules. We know when is a number x divisible by a number y? When the remainder is 0, right? So then only we say that x is divisible by y. So there are few divisibility rules to make things simple for us. What is the divisibility rule for 2? When I say what is the divisibility rule for 2, what I mean is that when can we say that a number is divisible by 2? We can say that a number is divisible by 2 by just checking the last digit of the number. If the last digit is divisible by 2, we say that the number is divisible by 2. So for example, you have a very big number a, b, c, d, e, f, g, something like that, and in the last you have 3, right? You just see the last number and you are sure that this number is not divisible by 2. Had it been 4 here, you are sure that this number is divisible by 2. So we have to just check the last digit and say whether, and we can say whether the whole number is divisible by 2 or not. Now let's come to divisibility test for 4. It says we have to check the last 2 digits. If the last 2 digits are divisible by 4, then we say the whole number is divisible by 4. For 8, its last 3 digits. For that matter, for any any number which is 2 raised to power n, if we have to check whether a number is divisible by 2 raised to power n, we have to look for last n digits, and if last n digits are divisible by 2 raised to power n, we say that the number is divisible by 2 raised to power n. This is how we check for any power of 2. Now let's come to divisibility rule for 3. It says sum of the digits should be divisible by 3. So let's take a number. Let's say a, b, c, d, e, f is a number. So to find whether this is divisible by 3 or not, what do we do? We would find the sum of digits, which is a plus b plus c plus d plus e plus f. If this number which we get after adding all the digits is divisible by 3, we would say the number is divisible by 3. For example, let's take a number 1, 2, 3, 4, 5, right? Sum of the digits are 1 plus 2 plus 3 plus 4 plus 5, which is 6 and 10, 15. Sorry, 15. Again, 15 can be written as 1 plus 5, which is 6. Now 6 is divisible by 3, and hence we would say 1, 2, 3, 4, 5 is divisible by 3. It's that simple. We have to just find the sum of the digits. If sum of the digits is divisible by 3, we say the entire number is divisible by 3. Similar is the divisibility rule for 9. So 9 and 3 have similar rules. So for 9 you have to again add the the digits of the number and see whether that sum is divisible by 9 or not. For 5 it's very easy. You have to just check the last digit. If last digit is a 0 or a 5, then we say that the number is divisible by 5. For 6, the number should be divisible by both 2 and 3. So we have to check for the divisibility of 2, we have to check for its divisibility by 3. If both the conditions are met, we say that number is divisible by 9. For 10, again it's very simple. You have to check the last digit. If last digit is 0, then we say the number is divisible by 10. For 11, the rule is slightly complex, but nevertheless it's easy. You have to find the sum of digits at odd place, then you have to find the sum of digits at even place. You will get two numbers, then you would subtract these two numbers. If you see that the resultant after you subtract these two numbers is divisible by 11, we say that the entire number is divisible by 11. Let's take an example to understand it, right? So check whether 5 4 4 5 is divisible by 11 or not. So 5 4 4 5. 5 is at first place, so it's an odd place. 4 is at second place, an even place. another 4 is at odd place, and this is even. So sum of digits at odd place is this 5 and this 4, right, which is 5 plus 4 9. Sum of digits at even places, this 4 and this 5. So 4 plus 5 again 9. Subtracting this, so we'll make say this is 1, this is 2. 1 minus 2, 9 minus 9, 0. 0 is divisible by 11, right? So we say 5445 is divisible by 11. So if the number digits are again if we increase the number of digits, let's say we put 2 and let's say we put 2, so this becomes, this 2 is at the odd place, right, is at the odd place. So we'll add it here and we'll get what, 11, right? And now here we get 11 minus 2, 2. Now since 2 is not divisible by 11, we say 54452 is not divisible by 11. It's that simple. Now let's see how in an exam we can use the property of, we can use these divisibility properties of various number to answer a question. So let's assume that we are given a question that a 3-digit number is divisible by 4 and sum of its digit are 9. How many such numbers are possible, right? Now when we see this, that it's always divisible by 4, it means that the last 2 digits are always divisible by 4, and the first digit or the 100th digit we have to find, right? The other condition is sum of the digits is 9, right? So the last 2 digits can be what? Last 2 digits can be 04, 08, 12, 16 up till 96 and finally 00. These can be the last 2 digits, right? So all the multiples of 4 beginning from 4 to 100, right, they are 25 multiples. So last 2 digits can be last 2 digit has these 25 possibilities, right? Now we have to find the first digit, which is the 100th digit. The other condition which is given is that sum of the digits is 9. So a plus 0 plus 4 should be 9. So a can only be 5, right? So this can be possibility. This can be a possibility, right? This can again be a possibility. This can again be a possibility. This can again be a possibility, and this can again be a possibility. But we see A28 cannot be, because 8 plus 2 is already 10, and if we add a in this, we would get a sum which is greater than 9. So this is not a possibility. Is A32 a possibility? Yes. A36? No, because 3 plus 6 is 9, and if we add a should be greater than 0, right? A cannot be 0. So a should be at least 1. So if we put 1 here, we would get the sum of digits as 10. So which is not required. So it's not a possibility. This is a possibility and this is a possibility, right? This is not a possibility. This is a possibility. This one is again a possibility. This is not. Again this is not. This is not. So if you see, all of these are not, and finally this is the possibility. So how many numbers? 1 2 3 4 5 6 7 8 9 10 11 12. So only 12 such cases are possible, or rather even this is the possibility, right? So you have to be very vigilant while doing these kind of questions, right? So there are 13 possible numbers which are divisible, which are 3 digit, which are divisible by 4, and at the same time have sum of the digits as 9. So there are 13 such cases. In this way, if you understand the divisibility properties, many questions become very simple for you in exam. This is how we use divisibility properties for solving various questions. Now let's go to some important rules for divisibility. First rule says if x is divisible by 2 or more than two co-prime numbers, it is divisible by their product as well. So what are co-prime numbers? Two numbers are said to be co-prime if they do not have any common factor other than 1. So let's say one number is 9, the other number is 8. There is no common factor, right? The only common factor between these two is 1. So we say 8 and 9 are co-prime. So now let's take a number which is divisible by both 8 and 9. 144 is such number. Is 144 divisible by 9? Yes, it is. Is 144 divisible by 8? Yes, it is again divisible by 8. So by this rule, 144 should be divisible by 72, which is the product of these two numbers, and which is true. 72 into 2 we get 144. So 72 is, for 144 is divisible by 72. Few other properties which may or may not be very useful in your exam, but yes, it's always good to remember that if x and y are two numbers divisible by p, then obviously x plus y is also divisible by p, x minus y is also divisible by p, x multiplied by y is also divisible by p, or rather I would say it is divisible by p square. So just keep these properties in mind. The more important and more pertinent properties are of remainder, rules of remainder. So if we have p as a divisor, d1 and d2 as two dividends, such that we get q1 and r1 as remainders in first case, q2 and r2 as quotients and remainder in second case. What would happen when we use properties like multiplication, addition, subtraction in this? Let's see. Let's add d1 plus d2. What we would get is p multiplied by q1 plus q2 plus r1 plus r2. So now if we divide d1 plus d2 by p, what would be the remainder? That's the question, right? We can see that this product, this is in the form of divisor into quotient, right? And this is the remainder, right? So the remainder would be r1 plus r2 if r1 plus r2 is less than p. If r1 plus r2 becomes equal to p, then we would take a p common out of it, and our quotient would become q1 plus q2 plus 1. So it would be 0 if r1 plus r2 is equal to p, and it would be if this r1 plus r2 is greater than p. A remainder cannot be greater than the divisor, so we have to divide it by p, and whatever remainder we would get from that division would be the remainder of d1 plus d2 also. So in this way, this is how we proceed if we have to add two dividends. Similarly, the rules are same even if we subtract two dividends, and the rules would be same if we multiply two dividends. If we subtract two dividends, the resultant would be minus, right? So we have to check for r1 minus r2. If we multiply these, the remainders would also be multiplied, and we have to check for r1 multiplied by r2. This is how we proceed in case we have to add or subtract or multiply the dividends, right? Let's see how do we get questions from this topic. So this question says we get a remainder 5 when 32 is divided by p, and 3 when it is divided by when 17 is divided by p. Also when 49 is divided by p, we get a 0 remainder, right? Find p. So we can write 32 is equal to p into q1 plus 5, 17 is equal to p into q2 plus 2. Also 49 is equal to p into q3. If we just observe, we see that 49 is nothing but sum of 32 and 17, right? So if we add these two, what do we get, right? We would get 49. So 49 is equal to, and there is 0 remainder, which means what? Which means r1 plus r2 has to be equal to p, as we studied earlier, so that it gives 0 remainder. Hence p is equal to 7. This is how we would proceed for these questions and solve it. The next question says what is the remainder when 32 raised to power some power is divided by 31. Now we know that remainder of 32 when divided by 31 would be what? It would be 1, right? Now what are we doing? We are just multiplying 32 442 times, right? That's it. So what is the remainder when 32 into 32 is divided by 1? It is divided by 31. It again is 1, right? And so on. We'll find that even if we keep on multiplying, the remainder remains the same, which is 1. Thus we'll get 1 as the answer. This is the, I think, the most basic question which can be asked from multiplication of remainders, right? You would be given numbers in such a way that generally you would end up in 1 as an answer. Otherwise, if you get something like a 2 or a 3 or a 4, the question becomes a bit complex, and I think, according to me, it would be out of purview of our CSAT exam. So we are not going to touch that right now. Maybe later, if we get some time, and if we like to delve deep into this concept, we can touch base that as well. Now the last concept of today would be last digit. So let me pose you a question. What would be the last digit of 23 plus 842? We'll just work with the last digits of 2. So we add 3, we add in 2, and what would we get? We would get 5. So 5 is the solution. What is the last digit if 23 into 842 is multiplied? Again, we would work with last digits only. 3 into 2, 6. 6 is the solution, right? So to find the last digit, we would only work with the last digit even if the number is very big, right? Now let's find the last digit of this expression, right? So the last digit of this expression would be last digit of 3 into 2 plus last digit of, so we are taking last digits here, 4 4 4 6 7. So 4 4 4 6 7, right? So last digit of 3 into 2 is 6. Last digit of this would be 4 into 4, we get 16. 4 into 6, we get 24. And 7, we just write as it is. So again, we would take the last digits here. So it would be 6 into 4, right? And again 7 as it is. So 6 into 4 becomes 24. We'll take the last digit 4. 4 into 7, we'll get 28. The last digit is 8. So 8 into 8 plus 6 is 14, and the last digit is 4. So the last digit would be 4. Now I would like to introduce a slightly complex concept of cyclicity. I'll again start this with a question, right? What is the last digit of 2 raised to power 500? If we have to do this, right? We cannot simply keep on multiplying 2 500 times, right? It would be a very tedious task, and we might end up doing this question only for the entire paper. So let me just check what happens when I increase the power of 2. What is the last digit of 2 raised to power 1? It's 2. What is the last digit of 2 square? It's 4. 2 cube would be 8, and 2 raised to power 4 would be 6. Now if I take 2 raised to power 5, surprisingly again the last digit is 2. 2 raised to power 6, the last digit is 6. 2 raised to power last digit is 4. 2 raised to power 7, last digit is 8. And for 2 raised to power 8, last digit is 6. So what we see is that after every fourth power, the digits are repeating, the last digits are repeating. So after every fourth power, so we say that 4 is the cyclicity, or 4 is the cycle of this 2, right? So after every fourth power, the last digit would repeat. Now how to find the last digit? We'll find the cycle. The step 1 is find the cycle of each number. So here we are finding the cycle of 2. Similarly, we will find the cycle of 3 or 4 or 5 or so on. Now we know that cycle is 4. Now divide the power which is given in the question to find the remainder. So we would divide this 500 by 4, and what do we get as remainder? We get 0 as remainder, right? Step 3. If remainder is 1, the last digit would be equal to n raised to power 1. So if we had got a remainder which is 1, the last digit would be equal to 2 raised to power 1, which is 2. If the remainder was 2, we would have just checked the last digit of 2 raised to power 2, and that would be the answer. If remainder was 3, the last digit would be what is the last digit of 2 raised to power 3, and so on and so forth. But if the remainder is 0, then the last digit is equal to last digit of n raised to power cycle. So our cycle is 4. Here we are getting a 0 remainder. So the last digit would be equal to the last digit of 2 raised to power cycle. Cycle is 4. So 2 raised to power 4. We'll just check the last digit of 2 raised to power 4. It's 6. Hence our answer would be 6 for this particular question. Right? Hence our answer would be 6 for this particular question. In this way, if you check the cyclicity of various numbers, you would come to these conclusions. Cyclicity of 3, 4, 7, 8 are 4. Cyclicity of 0, 1, 6, 5 is 1. Cyclicity of 4 and 9 is 2. So if any number which ends with 0, 1, 6, 5 is raised to power is raised to a certain power, you would always get that number as an answer. So if we get 6 raised to power 1, the last digit is 6. 6 square, the last digit is 6. 6 cube, the last digit is 6. Even if the number is something like 826 raised to power 826, what would be the last digit? It would be 6 always, right? Just check the cyclicity of these numbers yourself, and if you have any doubt, you can anyways come back to me. This is all for the number systems as of now. We have covered the entire number systems in 2 sessions. The questions of number systems would be given in an assignment which you would have to do. If there is any additional concept which comes in those questions, we would cover that in our solution video. I hope that you are clear about what to study in number systems, and you are very clear about the concepts we have discussed here. We would be uploading our next session on HCF and LCM very soon. Till then, even if you do not get the concepts right, just see the video again. Even if you have any doubts, you can just drop me an email or call me. I am available for any of your doubts. Thank you, and all the best for your preparations.